to Science, you guys. We are starting a new unit today, and our new unit is going to go over forces and motion. So we're going to be talking physics this 6 weeks, and it's going to be super fun. But we do have to start out with some notes, so I know that is not super fun, but it's what we have to do first. So we're going to start with our notebook where we have 2 pages side by side that we can actually write on, because it's going to take a little bit of room because I like to do drawing notes for this one. So we are going to first title our page Forces. And the first thing we have to answer is the question, well, what is force anyways? So what is force? So write that down. And you should have learned back in elementary school or even 6th grade that a force is a push or pull. So no matter what's happening, it's either going to be pushing you or pulling you to change an object's direction, to change its speed, or even to change its size. So let's put under here a push or pull to change. And let's do like this. 1, speed. 2, direction. Or 3, its size. So whenever we're thinking about this, if I'm pushing or pulling something to change its speed, that means I'm making it go faster or slower. If I'm pushing or pulling something to change its direction, so I'm changing where it's headed or coming from. And if I'm pushing or pulling it to change its size, think about like taffy, where you stretch out a piece of taffy and it becomes long, or a rubber band or a slinky or something like that, or squishing Play-Doh to make it into a more condensed version of a shape. And one thing we also need to add here is that we measure force in newtons. So measured in and we're going to write a big N, which means newtons. Now, we measure in newtons because, well, force was something that was come up with by Sir Isaac Newton. So I'm sure you've heard the story about he's sitting under an apple tree and the apple falls and hits him in the head. And he says, I wonder why that apple fell. It was a force. And I'm going to call that force gravity. So the apple falls and hits him in the head. He called it gravity. A force pulling everything towards the earth. You know, I don't know if that story is 100% true, but it's a pretty good example of it. But yes, gravity is a force that is pushing or pulling everything down to the earth. Let's see. Let's draw an arrow, and let's talk about changing speed. So let's say you hit a golf ball, and however hard you hit it with your club is how fast the ball's going to go. So a change in speed would be applying that force to push it in that direction. So let's use that as our example. Hitting a golf ball with a club. Let's talk about here. Let's put changing direction. So let's say you're playing soccer. Soccer ball comes at you. You kick the soccer ball back into play in the other direction. So changing their direction. So let's use that as our example. Kicking a soccer ball into a goal. Let's say that. And then the last one, a change in size. Or you could even put the changing of a shape, same difference. And we talked about how we could take Play-Doh or taffy and stretch it out long. We could squish it into a ball. We could take a spring like a slinky and we could stretch it, or we could push it tighter. So let's say, either one of those will work. So let's say pulling clay into a long strip, or forming it into a ball. All right, so I got a little sidetracked there for a second with the Newton story, but that brings us to our next section here, which is we're going to talk about something called net force. So we just talked about what is force, and we said it's push or pull, and now we're going to talk about net force. So right here, I want to put over here in this corner nice and big, or this side, net force. And we're going to it's going to be overlapping our page right here. Unless you write smaller than me, you're probably still on one page. So let's talk about net force. Let's draw it in picture form. So let's say I am playing tug of war. And my job is to pull the rope. So I got my little guy. Sorry, he's cute. Okay, so he's going to pull the rope one direction. And let's say the other person does not know how to play tug of war. And they come along and they push. And they're pushing in the direction that I'm pulling. So eventually that means they're going to work together. Now this would be a net force. That we would be combining a pushing force and a pulling force together. So this guy's going to be pushing and this guy's going to be pulling. Net force basically means the combination of the two. So a pushing force and a pulling force, they're going to work together in this case to help move the object. So we would actually use these two forces and add them together. Okay, so when I'm talking about add them together, the best example of this would be we're going to calculate how much force. So let's say he's pulling with 10 newtons of force, and this guy's pushing with 10 newtons of force. So 10 newtons and 10 newtons in the same direction gives you 20 newtons of force. So those combined forces are going to cause this box here to move. So let's write inside the box now. Forces in the same direction are added to get net force. And net force means the combination of the two. So why don't we do this? Let's add under here since we didn't do that yet. Let's add under net force a combo of all the forces on an object. That'll help us. Now let's say we have the same two guys. So we're going to draw our little dudes again. But this time we're going to be pulling in opposite directions. So he's going to be pulling one way. Oh, that's turbo box. That's all right. And then this guy, he's going to be pulling this way. I cannot draw. And with these two guys both pulling, and be like really working hard here, we're going to be pulling in opposite directions. So this guy is going to be pulling with 20 newtons in one direction because he's going to be stronger. And let's say this guy is only pulling with 15 newtons in the opposite direction. So this is more like tug of war here, where one's stronger than the other. And in this case, our forces are opposite. And when they're opposite, we're going to subtract them from each other. So this guy with 20 newtons of force is working against this guy with 15 newtons of force. So if you do 20 minus 15, well, this guy's going to win. And his net force is going to be 5 newtons. So this box is actually going to move in this direction. So let's put in our box here, let's put forces in different directions, or opposite directions get subtracted. And we're going to be doing work on forces and calculating forces today. So we're going to be working on looking at net force, which is either you add them up or you subtract them. Now, once we talk about net force, then we have to talk about two other things. So I'm going to move this way. We are going to talk about balanced forces versus unbalanced forces. So we're going to split our page down into two here for a second. So let's talk about what balanced means. So we all know if something is balanced, they're equal. And unbalanced would mean unequal. So when we're talking balanced forces versus unbalanced forces, we're going to say, are the forces equal or are they not equal? So over here, under balanced, let's write equal in force. Over here, let's write not equal in force. So we're going to be comparing the two for a second. Let's see. Over here, if they are equal in force, that means we're going to have no change in speed. But over here, there would be a change in speed. Balanced forces, you would have no change of direction because it's balanced, it's equal. But over here, definitely would change the direction. And then last, no change in shape. But unbalanced forces, you would get a change of shape. And then let's just draw our picture here. So let's say, and I'm going to make it a very simple picture. Let's say we have our box here, and one person's pulling to the left and one person's pulling to the right. So we're going to write down pull. And let's say this guy's pulling with 10 newtons of force, and this side's pulling with 10 newtons of force. Now remember, if they're equal, nothing moves. So this box is virtually going to stay in the same place. But we need to calculate net force. And since they're opposite in direction, we are going to subtract. So we're going to say 10 newtons to the right minus 10 newtons to the left gives us a net force of 0 newtons. And that 0 tells me we are balanced. We are not moving. There's no change in shape, speed, or direction. We are equal to each other. Now, on our unbalanced force picture here, let's draw our box. Again, they can both be pulling against each other. And let's say we have 50 newtons of force over here, but on this side we have 70 newtons of force. So whenever we go to find our net force, we're going to have 70 newtons left minus 50 newtons right, which should give you 20 newtons difference. So, after you figure this out though, we have to figure out, well, which direction is that object going to move? So when we look at this, you have to look at the stronger force. So our stronger force is 70, which is to the left. So our box will move 20 newtons to the left. So basically, force is actually pretty simple. It's either balanced or unbalanced. You either change the speed or you don't. You change the direction or you don't. Or you change the size and shape. And we figure all this out with our net force, our push or pull difference between the two. Now let's talk about one more thing before we get too far into this. So we talked about my little spill there about gravity. So we're going to actually turn the page here. And I'm going to write on the back of this one. So there are different forces. Like we said, we talked about gravity. And gravity is a force that pulls everything to the center of the earth. There are also other forces like friction, magnetism, electrical force, air force, not the air force that we're, going to have protect us, but air force as in air resistance. Okay, so let's go ahead and we're going to break our page in half, and then we're going to make 6 boxes. Zoom out a little bit. So in this box, let's write types, or actually let's write it up here, types of forces. And let's start with the easy one, gravity. And I like to do this with drawing notes. So gravity is going to pull everything to the center of the earth or towards other objects. So around our arrows, let's kind of draw a circle. And then we're going to put our continents. And they don't have to look beautiful, but, sort of like a continent here. There we go. So gravity pulls everything towards the center of the earth. Let's go up here to this top box. let's talk about friction for a second. So friction is a force that comes from more than one object rubbing together. So think about like if you put your hands together and you go back and forth like that, you get the warm feeling between your hands, and that is because you're applying friction. So friction between your skin creates warmth. So let's do this. Let's see if we can draw little mitten hands here. So we have one hand. Oh, this is going to be terrible. And then we have the second hand. Little chubby hands. And in between them here, we are going to have friction. And because I can't even tell what I've drawn here, I'm going to actually write what I drew. So our hands rubbing together cause friction. Let's talk about like a marble or a ball. I know this is going to sound weird, but let's say I roll a ball across a tile floor versus I roll a ball across my carpet. This is also a form of friction. The tile is going to have less friction. The carpet is going to have more friction. So friction can actually cause a change in speed. It could actually cause so much of a change in speed that it stops the object. Let's go right down here. Let's write electrical. Now I know we don't think of electricity as being a force, but I want you to think about static electricity, especially right now with the weather changing outside. You go to touch metal and you go, ah, it shocked me. That's actually electrical friction. So electrical friction is because you have a buildup of electrons on an object. So whenever you have a positive electron count on your hand, but the door or the metal has a negative electron count, meaning it's very unhappy, and you go to touch it, it sends out a shock to you. So let's see, best way to draw this one. Let's draw a plus sign as your head. Because you're happy, you're positive. And let's draw a door. And a doorknob. And it's going to be a minus sign. So put a minus sign next to the door. And whenever you go to touch the door, zap, 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 it electrocutes you. Or shocks you. It doesn't electrocute you. That's a bit intense. It shocks you. Let's see. Let's go to the bottom one here. And let's go ahead and do air resistance. Now, when I think of air resistance, I think of the size of things or the shape of things. So, let's talk about like a feather. So we have a feather. So we're going to draw a little feather here. Now my feather has all these little soft spikes coming off of it, which means it's going to have more air resistance. And let's say I drop that feather. Well, that feather is going to actually take forever to hit the ground. And that's because all of these little fluffy pieces are causing air resistance. And let's say I drop a basketball or baseball. Baseball is easier to draw. A baseball is actually going to fall straight down to the ground because it's going to have less air resistance. It's going to be smoother. It's going to not be affected as much. So let's, under the ball, put less. And under the feather, more. And last one up here at the top, let's do magnetism. So we got magnetism. Now, magnetism is one of these where opposites attract. So let's draw like old school magnets from when you were a little kid. So you have a North Pole and a South Pole. And then on the other side, you're going to have a South Pole and a North Pole. Now these two are going to want to stick together. They're going to connect. And they're going to make one happy magnetic bar because opposites attract. So they're going to stick together. Now sometimes magnets, or all the times actually, magnets are going to repel each other when the north side is facing the north side. So north and south again, but we're going to switch this one around and it's going to be north and south as well. So whenever you're faced with this situation, this is going to repel. So here we're going to attract, and down here we're going to repel. They are not going to want to stick together. And usually when you get those magnets and you try and stick them together, they try to stick something like opposite of each other because it really wants to be over here with the south side, but it can't get there. So these are all forces we're going to be talking about that can affect our net force here. So I hope you have written down these notes in your journal. It should be fairly simple. Lots of drawing today. And then you're going to do the work attached. And if you have any questions, email me, or I guess we can call it texting online. You can do the little private comment. All right, so write that down and get started on your work.